Hello, and thank you for joining us, and welcome to our webinar today. It's titled Opportunities and EM&V for Improving Electricity Distribution Efficiency. This webinar will run for about 75 minutes, during which time we'll have 4 presentations. All phone lines for the audience are muted. If you do have questions, please type them into the text box, and we'll do our best to get them answered during the webinar. The webinar is also being recorded. The recording and slides will be available at the LBL webinar website, and that website's listed on this and other slides of the presentations. And we'll get those up perhaps as early as today. Funding from the webinar is from the U.S. Department of Energy's Office of Electricity Delivery and Energy Reliability. And LBL is coordinating this series with input from and in collaboration with DOE and the U.S. Environmental Protection Agency, the National Association of Regulatory Utility Commissioners, and the National Association of State Energy Officials, all of whom I want to thank for their support. So as an introduction, please let me start off by introducing myself. My name is Steve Schiller, and I'm an affiliate and senior advisor in the Electricity Markets and Policy Group at Lawrence Berkeley National Lab here. I've worked in the energy industry for many years, and with a great deal of that time focused on efficiency, demand response, and distributed generation. One of my areas of expertise is in evaluation, measurement, and verification, and I'm fortunate to be the facilitator of this webinar series. LBL is hosting these webinars as supported by US DOE, as I mentioned, and LBL itself conducts non-classified research and is operated by the University of California. LBL, also with funding from the Department of Energy, provides technical assistance to states, primarily state energy offices and utility regulatory commissions. This webinar series is part of that assistance, but we also provide specific assistance for individual states. Before I say a few words about that assistance, let me just mention the disclaimer below here, which essentially says the DOE and LBL and the University of California, and probably anyone who's ever known me or ever will know me, does take any responsibility for what myself or other speakers will say today. In terms of the technical assistance, LBL provides that independent and unbiased assistance for state utility regulatory commissions, state energy offices, as well as tribes and other regional entities in a wide range of energy areas such as efficiency and demand response, renewables, and a number of grid topics. Contact information for the technical assistance is available via the websites listed, and those will also be available for those who don't write too fast on the webinar website. And if you really don't write fast, you can just Google LBL EM&V webinars. This webinar series is designed to support activities for documenting energy savings and other impacts of efficiency programs. As mentioned before, it's funded by DOE, and I want to thank EPA and NARUC and NASIO and organizations such as the several regional energy organizations, the Consortium for Energy Efficiency, and the International Energy Program Evaluation Conference Organization, who all help with the outreach. And by the way, IEPC, the evaluation conference, has their abstracts open for up till November 11th for their every 2-year EM&V conference. So as I've mentioned, our target audience is those utility commissions and state energy offices, but we also hope this is of value to many others, and of course everyone is welcome. There will be some more webinars coming forward, and the information will be contacted on the webinar site. For our next webinar, it's tentatively scheduled for early December on evaluating non-energy impacts of efficiency projects and programs, and we'll hopefully be having many more into 2017. So let's move on to today's webinar. What I'm going to do is first provide some brief background, some thoughts on EM&V for these distribution system efficiency applications. Next, Tom Short of EPRI will provide about a 20-minute introduction to energy efficiency conservation voltage reduction, which is known as CVR, and voltage and volt-ampere reactive optimization, which is also known as VVO, as well as a little bit about state experience with CVR and VVO. Next, we'll hear about an example CVR project with some focus on how the impacts were assessed from Jim Parks of SMUD. And then we'll conclude the formal presentations with Josh Rustin, talking about the Northwest Regional Technical Forum's EM&V experience and the measurement and verification methodologies they developed for CVR and VVO. We may have some time for clarifying questions after each of these presentations, and we're also scheduled for some time at the end to have responses to your general questions that you can provide, again, via that text box. Since, as again, all the lines are currently muted, but you can use those text boxes to communicate with us. And again, it's being recorded, and they'll be available up on the website. So let me get into some background on the T&D system, just to sort of set the page here for our webinars. So the transmission system, that's the system that moves large amount of power over long distances at high voltages, whereas the distribution system refers to delivering electric energy from the high voltage transmission grid to specific end-use locations such as homes or factories, office buildings, etc. This figure here from the Federal Energy Regulatory Commission, FERC, shows the basic structure of the electric grid. The difference between the amount of electricity that is generated at the power plants and the amount that is consumed is end up being made up by losses in this T&D system. So this webinar is going to address the state of art with respect to EM&V, i.e. the documentation of energy savings associated with actions taken to reduce these losses, therefore the T&D energy efficiency. According to the Energy Information Agency, national annual T&D electricity losses average about 7% of electricity that is transmitted in the U.S. With the U.S. consuming something on the order of 4 billion megawatt hours per year, those T&D losses, let's just say assuming 10 cents per kilowatt hour, are worth about $25 billion a year. And other sources put the losses in the range of 6 to 10%, with recognition the losses vary depending on a wide range of factors such as weather, the voltage, the distance from the consumer from the generation source. And this figure here shows one estimate of typical losses in the T&D system, showing an even greater range because it is site-specific and condition-specific. Now, within the T&D system, there's opportunities for reducing losses both in the distribution system and the transmission system. I'm not going to go through these bullets, but I just want to list them, and again, these slides will be available, just some of the ideas of things that can take place. During this webinar, we're really going to be focusing, though, on the distribution system. And now I'm going to finish off my quick presentation here with some points about the documentation, or the EM&V, for T&D efficiency. These are some thoughts that will be discussed through our other presenters, and they'll have their own points of view and nuances on these comments. But I wanted to set the table here with these points. First, that T&D EM&V is conceptually straightforward, but in practice, like many things, it can be pretty complicated and thus expensive to determine reliably the energy savings. With the cost and complexity of doing this, a function of the actual measures being taken, the scope and the scale of the effort, the type of loads that are served by the T&D system affect the savings in the EM&V processes. Of course, the accuracy and reliability of how well you're planning to determine these impacts. And an important aspect of this, too, is whether the energy savings that you're looking at is just for the T&D system in isolation, or really looking at the T&D system in combination with the generation system for an overall package. You can end up with some different perspectives and results depending on, again, whether you isolate the T&D system or look at it in combination with the generation system. Next, the T&D practices for EM&V, describing them our best practices is really, it's a work in progress. But the progress seems to be accelerating with some push from some national and regional and state authorities. And these protocols for determining these impacts, can be tested with the output being hopefully more established in presumably reliable ways to document the impacts. The third bullet here, isolating and documenting the impacts of distribution system efficiency as compared to transmission system efficiency tends to be more straightforward. And again, that's going to be the focus of what we're going to talk about. And then specifically on this last bullet here, we're going to be looking at EM&V for conservation voltage reduction and VVO, or voltage optimization VO. Those are probably the most advanced of any category of T&D efficiency actions, with several past and ongoing efforts, and that's what we're going to be focusing on today. So with that, let us turn to our other presenters. And first up will be Tom Short. Tom's a Senior Technical Executive with the Electric Power Research Institute, EPRI. He has over 25 years of experience working in the area of power distribution. Tom led a portion of EPRI's Green Circuit project that looked at distribution efficiency, and he authored the Electric Power Distribution Handbook by CRC Press in 2014. He has a master's degree in electrical engineering from Montana State University. So with that, Tom, I'm going to let you take it from there. Thank you very much.
Thanks, Steve. So I'm going to give an overview of what I see in the utility industry and approaches for distribution efficiency mainly, particularly focusing on CVR and VVO, which Steve mentioned. And so utilities have, as Steve showed, they have losses, and they have different programs that they can go after to improve efficiency. And for this talk, and for most of this session, we're going to focus mainly on conservation voltage reduction and VAR optimization. And both of those terms, both of those programs, they're kind of the same thing. And the efficiency gains you can get from that program or those programs, they dwarf the other options that utilities have for improving their efficiency. So I mentioned reduce line losses. Line losses are a component that, at least on the distribution side, that might add be a couple percent of the total transferred electricity. So if you're reducing those losses, you're reducing something that's only 1 or 2% to start with, and so the gains you get are pretty small. But the gains you can in efficiency, over what I'll call societal efficiency, overall energy consumption, are much bigger with conservation voltage reduction and volt-VAR optimization. Because those programs, they not only can improve the efficiency on the utility side, they can also improve the efficiency on the end use side. So that's why the top two programs there are of such focus in the industry today, because that's where we can most economically get energy savings. So there's been quite a bit of industry work on the use of voltage reduction, CVR, volt-VAR optimization, any of those terms. The bottom line, the jury's already come back, and it's pretty much a settled science that the idea of reducing voltage will reduce consumption and improve overall societal efficiency for the delivery and use of electricity. So one of the first big efforts was performed in the Pacific Northwest. NEA, the Northwest Energy Efficiency Alliance, they did a great piece of work where they had several field trials in the Pacific Northwest. And all the documents that you have on the screen, they are public documents, although the link I had for the NEA document's broken, so some quick Googling, I couldn't find a fixed version of the link, so one might be harder to find. So PNNL had an important study surveying the opportunities in the U.S., and I was involved quite a bit with the last one, where EPRI did several pilots at different utilities and did quite a bit of modeling to evaluate the best ways to implement distribution efficiency and look at the opportunities there. So just starting with a couple of definitions, more information on what CVR is. Really the idea is that the utility reduces voltage, and when a utility reduces voltage, then that reduces voltage at the outlets that everything's plugged into, and so the equipment sees lower voltage, and quite a bit of equipment, when it has lower voltage, it consumes less electricity. So that is the idea behind voltage reduction. Utilities can use it all the time. They can just use it at peak times. But that's the bottom line behind reducing consumption, is to reduce voltage. Now, volt-VAR optimization, that program, the idea is to use voltage control and VAR control. And VARs are called reactive power. And in the actual equipment that does that, utilities have what are called voltage regulators that they can use to raise and lower the voltage, and they also have capacitor banks. And the capacitor banks control reactive power, and they also influence line losses and voltage. So utilities can control those in different ways, and when we do it optimally, well, put that in quotes, optimally can mean different things depending on what you're trying to optimize. But normally the way utilities apply this is that they're optimizing to lower voltage. But we don't want to lower it too far. We want to lower it just the right amount to maximize energy savings while not leaving some customers with low voltage. So really the terms CVR and VVO, oftentimes they're the same program. You kind of implement CVR with a VVO program. But some utilities might have a slightly different optimization than another. So some might also have a optimization that tries to minimize line losses, for example. So I prepared a bunch of questions, a sequence of questions, what I might call the frequently asked questions around voltage reduction and distribution efficiency programs. And so particularly focused on CVR, or voltage reduction, where do the savings come from? Now, as I said earlier, when you reduce voltage to equipment, a lot of it draws less electricity. Some of the biggest ones I've shown on the screen. Lighting is a huge component of a voltage reduction, a conservation voltage reduction program. When you reduce voltage to many lighting fixtures, you'll reduce the consumption. Now with lighting, you will also lower the light output. Some other equipment, like the transformers and in the upper left, or the motors in the bottom right of the screen, when you lower voltage to a motor, most of the time you're actually making it run more efficiently. It's running cooler, and so you're getting the same output for less input. So in the case of motors, you're not reducing the output, you're just getting an efficiency gain. And that's particularly true of lightly loaded motors, motors that have less mechanical loading on them. When a motor is running really hot with a heavy mechanical load, then there can be a kind of a sweet spot where you start lowering voltage and you might get some benefit, but then you lower a little bit more and then it starts to get worse. Now, air conditioners, I think, are a huge component of the savings from a voltage reduction program because of the motors in there. And we've seen that in a lot of our monitoring and measurement and verification studies. So next question I'll tee up. How much of the energy savings are on the utility side, and how much of the savings are on the customer side? Well, in a lot of our modeling, we're estimating that roughly 90 to 95% of the savings is on the customer side. It's the customer's appliances. It's their lighting. It's their refrigerators. It's their air conditioners. And the savings that does come on the utility side, that tends to be mostly in street lighting and in transformer losses, particularly the no-load losses or the idling losses. You see a link there. I put together a little calculator that if you can fiddle with a few variables and look at how it changes the split between the savings on the utility side versus the customer side. Really the bottom line is you can think of a voltage reduction program as a way of providing mostly end-use efficiency gains. Okay, next up, how much can we save from a voltage reduction program? How much is this CVR and VVO going to give us? Generally, we're looking at something like 1 to 4% of the electricity that's delivered, and where you fall in that range primarily depends on, well, what does your electrical infrastructure look like? Some of them it's easier to lower voltage than others. The PNNL report that did a nationwide survey and estimate, they figured that if you kind of did it everywhere in the U.S., you're looking at something like a 3% reduction. And their estimate, if you just did it on high value feeders, the easiest ones, the ones where you got the most benefit, then you could still get 2.4% energy savings across the board in the U.S. So there's quite a lot of opportunity there. And as an energy efficiency program, it generally rates very high on cost benefits. It doesn't take much investment to make significant gains from CVR or VVAR optimization. So how does a utility go about implementing voltage reduction? How do they implement these programs? Well, the easiest way is that utilities have voltage regulating equipment called a voltage regulator. And the easiest way is just to turn down the volume on that, just to directly lower the regulator settings. And it's a simple way, and it requires a little bit of engineering and analysis, but it's easy to implement. The problem with the simple approach is that if you lower the voltage too far on that setting, then you'll start to have customers with voltage that's under the normal band. And so remember, we're lowering voltage, but we still want to keep the voltage within the band of normal operations for equipment. So the next step in sophistication might be, okay, voltage regulators also have a mode of control where they lower voltage more at lighter load, and that is a way to help counteract the voltage drop, the drop in voltage that happens under heavy load. And so that's kind of what I'll call a second way. But then there are more advanced ways of controlling voltage. And one of them is that there are several commercial, what are called VVAR control systems. They control capacitors and voltage regulators, and they might have various types of monitoring and modeling, system models to keep track of everything and more optimally control the voltage, the VAR flows, and they can keep the voltage as low as possible to as many customers as possible while not giving some customers under voltages. And some of those systems also involve special meters that are put out at key points on usually the distribution system where the voltage is most likely to go low. So the idea is to keep an eye on that and keep pushing the voltage down, but still making it not go too low. Now, AMI meters, smart meters are a great way to provide that feedback on what the voltage is, and that's really nice because if you have coverage in an area, then your metering can be at every customer, so you can keep track of what's happening to the voltage at every customer, or at least a subset of those customers to make sure that most customers are still getting voltage within bands. The next level of sophistication is that you can also apply improvements to the distribution system that will allow you to more uniformly drop the voltage to customers. And so it generally directly translates that the lower the voltage, the greater the energy savings. So if we can make sure that the voltage is more evenly applied to customers, there's less voltage drop, we can get more voltage drop to more customers. And there are several programs. It's adding more capacitors, adding voltage regulators, balancing phases, even reconductoring. And in many applications, you can still justify pretty significant improvements in the electric utility system to make improvements to your ability to drop voltage. And a lot of these are economical if you compare CVR as an energy efficiency program to other energy efficiency programs like light bulb replacement programs. So who's doing what? EPRI has not done official industry benchmarking, but I have prepared a list of some of the utilities that are reducing voltage at peak times of the year. And the advantage of that is that that if you reduce loadings under the peak times of the year, it reduces the impact on equipment and can delay investments necessary to meet the peak loading. So the top two utilities on the list, they were both pioneers in pretty aggressive programs as far as squeezing the most out of the benefits you can get at peak by flattening voltage profiles and targeting and using capacitors and voltage regulators. But it's tricky to reduce voltage at peak because that's when the load's the highest and that's when you get the most voltage drop. And so you end up with, for example, maybe you have to have high voltages near the substation to supply a customer at the end with acceptable voltage, because as you go out from the substation out on a circuit, the voltage tends to drop. So being able to reduce voltage at peak can actually be trickier than doing it under lighter load conditions. Some of those utilities on the list came from the report that's highlighted there, so if you want more information, you can dig into their report. And there are also several utilities that that have pilots or are in the process of either implementing a system or applying for a rate recovery to start a program. So who's doing it full time? This is a smaller list. There's not as many utilities that are doing it full time. And I think that's mainly driven by the impacts on revenue, and that most utilities get their money by billing based on kilowatt hours. And if that is reduced by 1, 2, 3%, then that reduces the money that comes in by almost proportionally, depending on how the rate is set up. So if CVR is treated as an energy efficiency project and it can be included in a energy efficiency portfolio, then that can provide a way to counteract that impact on rates, and there's more of an incentive for utilities to make the investments to build a CVR VVAR optimization program. Okay, how can the energy savings be demonstrated? I think I'm going to punt on this one. The bottom line is it's tricky. We're talking about energy savings of 1, 2, or 3%, but the variability from day to day and year to year of the electricity consumption is quite a bit more than that. So you're really trying to tease out the savings from something that has pretty high variability. So I'm going to punt on that, but fortunately the next two speakers, Jim and Josh, are going to talk about this more. So what's going to happen to the savings in the future? That's an interesting question, because if utilities are going to invest in infrastructure to implement a voltage reduction program, volt bar control or whatever, then they need to know, well, how long is the benefit going to be there? I think the industry thinks that its benefits are going to go down, mainly because more and more of the loads are going to become electronic loads in some way. Most appliances that have a computer or electronic power supply are not voltage sensitive. They're what we would call constant power devices. They, at least within a normal operating range, they consume the same amount of electricity. And so we see that in lighting. The transition from incandescent bulbs, which are very voltage sensitive, to fluorescents, which are still voltage sensitive, to LEDs, which are not voltage sensitive at all, at least in the models we've tested. And the same thing happens on motors. If a motor is pretty voltage sensitive, but if that's converted to an adjustable speed drive with an electronic front end, then that can take away the energy savings you would get by changing the voltage that's on the front, because the electronics will just counteract whatever you did to the voltage up front. So we generally see this going down. The question is how far is it going to go down and how fast? And I think it just depends on how fast some of the changes to these new technologies happen. If LEDs dominate the market in 5 years, I think that's going to have a huge impact on the benefits from voltage reduction. We're currently doing a pilot study with the utility in Hawaii on volt bar control and reducing voltage. And the preliminary results so far show that we're getting less energy savings than we've seen in other parts of the country. So Hawaii may be ahead of us because Hawaii has high electric rates, very high electric rates, and that has probably driven more of the customers there to install more efficient air conditioners, more efficient lighting, and so that may be why we're seeing less benefit there than we've seen in other pilots. So seasonal effects. The answer is yes, there are seasonal effects. It tends to have more benefit in the summer and less in the winter. And I think the main driver in the summer is air conditioning. A lot of air conditioning, you get more savings from CVR. It's worse in the winter. If you have a lot of electric load in the winter, that electric load is normally controlled by a thermostat. And so even like an electric heater, it's a resistor. It's highly sensitive to voltage, but if it's temperature controlled, then even though you lower voltage, what's going to happen is that the temperature control is just going to make the heater run longer to make up for that. So overall, there will be less benefit in the winter than in the summer. And the most pronounced one is the published data from Hydro-Quebec showed that they get very low benefits in the winter because they have historically a very low electric rate, so they have a lot of electric heating, and in the summer those electric heaters just run longer, so lowering voltage doesn't really help. So I'm kind of running out of the questions I've got teed up here. The last one I put up there is, do savings differ by region of the country? There's still gaps of where we have pilots done throughout the industry, but overall it seems to be fairly uniform. Starting with the studies in the Pacific Northwest by NEA, to a lot of the EPRI studies were in the southeast of the U.S., and then there have been other utilities that have covered like the upper Midwest and other parts of the country, and it generally is we've seen savings across the country. Some areas maybe a little bit more than others, but there's not a huge difference by area. And so that's all the questions that I've teed up. I'm going to just ask Steve. I see that there's been a couple of questions come in on the chat line. Do you want to address any of those now or save them till the end?
Tom, thank you, Tom. That was great. And actually, some of the questions you started to answer as you went further into the presentation. We're running a little tight on time, but there is one or two that I want to combine and just ask you for a little clarification on, and that's the impact of the voltage reduction on the loads. You had clarified that it's, the resistant loads that reduce their consumption, whereas the constant power loads don't so much. But, what is the effect, say, on the motors of, reducing their voltage? Do they slow down? Do they become, do they have less torque? Is there something that happens to them that's the negative side of reducing the voltage on motors? And then also just a quick one on for the resistance heating, you described how that can or cannot reduce in savings. That might change if there's more switching to heat pumps, though, wouldn't it? Because those are driven by motors.
They are driven by motors, but there's still some temperature effects that work against you for heat pumps. So even though a heat pump is an air conditioner run backwards, that there are some I'll call them second order effects, but they're big effects that work against you in the winter, so that you get savings from a heat pump, but not as much as if it's the same unit is operating as an air conditioner during the summer.
And then the impact on the motors of the voltage reduction?
Well, it's a little bit of a complicated question because it depends on what's on the mechanical loading side of the motor. But generally, at least especially the simple motors and motor control systems, there's the impact on the output you get from the motor is not affected much. Because remember, we're still not talking about huge changes in voltage. We're talking again 1, 2, 3, 4, 5% drop in voltage, and that still keeps the motor in kind of its sweet spot as far as its operational output. But in most cases, it tends to move it to a better sweet spot in terms of efficient operation of the motor. So the motor runs cooler and can get the job done with less input.
Well, thank you, Tom, and thank you for your presentation. We're now going to turn to an example program in Jim Parks of SMUD, who's, I was just going to summarize Jim's background as a wild and crazy guy. We've known each other a long time, but I think I should probably be a little more formal with that and mention that Jim is a program manager in the Energy Research and Development Department at the Sacramento Municipal Utility District, or SMUD. He currently oversees their efficiency, grid modernization, and electric transportation R&D projects. And he's recently completed a $308 million smart grid initiative with over 40 individual projects. And prior to his current assignment, he worked with emerging efficiency technologies, like transportation, efficiency program development, and efficiency program and transmission planning. And he has his degree, also in electrical engineering, with a number of years of experience in this industry. So Jim, if you can take it from there.
Thank you, Steve. And I'm pretty happy to be talking about this. It's kind of an interesting space for me because I've got a significant background in energy efficiency. And typically when I hear someone say energy efficiency, I'm thinking building efficiency of some sort, efficient air conditioners, lighting, building shell, that sort of thing. And so when I moved over into the smart grid space, I discovered this whole area of efficiency, this conservation voltage reduction. And it got me to thinking, I wonder if there's any way to do conservation voltage reduction and claim it as part of an energy efficiency program. So move on into this. Just a little background about SMUD. We're a muni, which means we don't make a profit. Any profit we make goes back to our customers in the form of lower revenues. And we basically serve Sacramento County, which is a 900 square mile service territory. And we have an elected board of directors that has 7 members. For our energy prices, you can see that our average residential price down here on the bottom, let me draw right here, 13.5 cents for residential on average, 12.5 cents for commercial. This didn't show up the way I'd hoped, but this is how CVR works. And if you look at the green line here, no, sorry, let's look at the blue line first. Sorry, the blue line is how voltage usually goes from a substation. You start up here on this side, this is the substation. You go out here to this end. This is the, the end of the line. And the voltage typically drops from the substation to the end of the line. So we do volt-VAR optimization to help lift up the voltage a bit, which is the green line here. And so what we do through the volt-VAR optimization, as Tom had said, we add capacitors, we add controls, we add communication to the line so that we can communicate with those capacitors and figure out what's going on the line. And so it, in essence, raises the voltage up, especially at the end of line. We're required to provide voltage between plus 5% or minus 5%. In the US, that's 120 volts, so you have a range of 126 to 114 volts. So basically, this is our bandwidth that we have to work with. We need to provide voltage in that range. So coming back to the VVO, we boosted up the voltage on the line, and then we come down and we can actually go to the substation and we can adjust the tap changer. And looking at this red line here, you can see that we can reduce the voltage across the line. What you end up with is, specifically in this area right here, you see energy savings. So if you do it according to the way this chart is, the people at the end of line probably aren't going to see as much CVR benefit as those at the start of the line. So as part of this American Recovery and Reinvestment Act project, we started out with conservation voltage reduction on 2 substations. We did a lot of different other projects. Some of them are listed here. But what we came up with, our early results on the project are up here in this side. You can see that on one substation we reduced voltage by 2% and we saved about 2.5% in energy. On the other substation we reduced energy use by about 1%. Now I would say that the 1% substation is really kind of within the bandwidth of error, so we believe we saved, but we can't say that for sure. Based on the results of this project, we went ahead and we did CVR on 14 substations. From that, we calculated what is known as a conservation or a CVR factor, a conservation voltage reduction factor. See right here, the CVR-F. We theorized that we could get between 0.5 and 0.7 CVR factor. Big deal. What's a CVR factor? Over here on the right-hand side, you can see it's basically a calculated value, and what you do is you take your CVR factor, you multiply it by the percent reduction, and you get the answer. So in other words, if I have a CVR factor of 1 and I do a 2% voltage reduction, I'm going to get a 2% energy savings. So this is what it looked like when we did CVR. The lines up on top here are the voltages, and so the red line is voltage before, blue line is voltage after, and then the line below you can see the load profile. And you can see that this space in here represents the energy efficiency, actually more like right in here. That space between the red and the blue lines represents the energy efficiency. And so you can see that there are real savings there. So what we did was we basically modified the control system at the substation to be able to do CVR, and we did 3 years of testing. We worked with EPRI on this, and they have a statistical model that allows them to predict the impacts and to calculate the results. And we took lots of data. We had our SCADA system, which stands for Supervisory Control and Data Acquisition. Basically, it's our visibility at the substation, which gives us two-way communication at the substation. We can get voltage reads and ampere reads and megawatt hour reads and those sorts of things. And so that all goes into the regression analysis. We basically were targeting 2%, but as you can see down here, we got about 1.8% average voltage reduction. We got a 2% average megawatt hour reduction and a 1.1% average load reduction. So our megawatt hours and megawatts were reduced. Here's the CVR factors for each of the 14 substations. So you can see that it ranges from up here from a high of 2, and down here is actually a negative 1, which in theory means that you're using more energy as a result of reducing the voltage. So these two were kind of outliers. If you look at basically the general equation for calculating the efficiency, power equals current times voltage. So if you reduce the voltage, you reduce the power. Now, if you're looking at something like an incandescent light load, you're also reducing the work. And so in essence, if you had a 100-watt incandescent light bulb and you reduced the voltage 2%, you would see a slight reduction in the lighting as a result of that. But as Tom pointed out, a lot of our loads are now moving to more of electronic modes like LEDs, and even the fluorescents are different. It's not a linear relationship, so it's hard to say exactly how those turn out. But on our 14 subs, we had an average here, you can see by this box, and then the average conservation voltage reduction factor was 0.6. So in other words, for a 2% reduction in voltage, we should see a 1.2% energy savings. And that's more of an average. I think I was proposing that for future projects at SMUD that we would use the 0.6 as kind of a deemed value. That we would just basically say, hey, the average is 0.6, and that's what we're going to use on every substation. Our goal was to actually test 3% voltage reduction, and we did that a couple of days, but I have to admit our system operators were a little concerned about deviating too much. So we really limited the main study to 2% voltage reduction. Did find out that when you're analyzing the data, there's lots of data, and it can get messy. So you find, like, you know, how are you supposed to calculate the CBR savings when your data looks like this? You know, you've got all these spikes and lows and valleys, and it's changing so much that sometimes it's difficult to calculate the savings. You also have things where for one reason or another something's tripped, or there's a little outage or something, and there's some issue on the system, and you need to go out and correct that before you can actually do the calculations properly, or you have to remove that data. So a few of the things, we did have difficulty explaining the CVR factor outliers, like why was one 2 and why was one negative. I mean, to me, a 2 CVR factor doesn't really make sense. I can't imagine reducing 1% and getting 2% energy efficiency savings. We didn't get any customer complaints. One of the things with this project, we did this study what I call blind. We had no, we weren't getting pinging the meters, we weren't getting any data back, so we reduced the voltage, and it was kind of, you make the assumption, if nobody complains, things are good. And you know, intuitively, that's not always the case. You know, people may have seen a little more flicker or something, I really don't know, but nobody complained. One of the things that I wanted to do as a result of this, and I never got around to it, was to look at why some substations perform better than others. So what were the characteristics on a given substation that yield higher performance? In other words, is it like commercial versus residential? Is it new buildings versus older buildings? Is it newer electrical infrastructure versus older electrical infrastructure? Is it the types of loads on the substation? Never got around to it, but I think it would be worthwhile, because that way you could actually target the substations that you want to do CVR on, and you could optimize the benefits, kind of the cherry picking thing. I think I'm probably going to be running out of time, so I'll kind of breeze through some of this. I want to get to some of the things on the end. We did determine that the model that we used, we felt like provided us a pretty good approximation of what was going on. And I feel like that if you remember the blue box that kind of had that bandwidth of and our CVR factor in the middle, I think that was kind of where everything should fall, and I think that was pretty accurate. EPRI performed a little cost-benefit analysis on the 14 substations. Now you have to look at this through energy efficiency metrics, because you are, in essence, losing revenues as a result of CVR. And you can see that the annual savings would go along in a, I can't call that a straight line, but it's, pretty flat. But cumulatively, the savings begin to accrue. Now, one of the things, well, let me look at this next slide first, because this is an interesting one. This is something that PNNL put together, and Tom talked about this also, but the different loads that you have on your system are going to yield different results when you do CVR on them. So you can see here, incandescent lighting, for a 3% reduction, you can get a 5% energy efficiency saving. Look at fluorescence. It totally varies, 2 to 8. So, which brand of fluorescent, which type, I don't know, but some will give you 2%, some will give you 8%. LED lighting, 0 to 6. That's kind of interesting. We're all going to LED. We might get a 6% savings, which would be, and that's a CVR factor of 2 on that technology alone. And then look at LCD and plasma TVs, 0%. Those have built-in voltage, I don't know what it is, voltage optimization. So if you reduce voltage, it will automatically compensate for that. And then air conditioning has got a pretty big range. So whatever you have on the system will impact your results. So the nice thing is, though, the energy is saved across the entire substation, but as my earlier slide showed, theoretically it could be more towards the closer to the substation rather than farther out. There's small energy savings for each customer, but the thing that's important to point out is they don't know it. It's invisible. So you, like as a utility, if you want to say, man, we're great, look at all this energy savings, the customer doesn't even see it. According to Senate Bill 350, which was the one that took our renewable portfolio standard from 33% to 50% and also doubles our energy efficiency goals, you can claim CVR as part of your program savings now. So that was kind of the bone they threw the utilities when they doubled their goals. Like I mentioned earlier, we performed our CVR pilots blind, and the next test that I would like to do would be to put Bellwether meters out there, ping our meters, really understand what's going on during CVR events. We are not operating CVR right now, and when we do models now, we're seeing lots of out-of-spec voltages. So for some reason we're seeing low voltages and high voltages, and really one of the reasons is that we found is grow houses. Interestingly enough, these people will go into a house, they'll install all these lights. You see this picture down here at this point? I mean, that is all infrastructure for lighting in a home, and that's way more load than a home was ever meant to have. Well, when you start doing an analysis and look at all the meters and the voltages out there, you're suddenly seeing high voltages and low voltages, and you come and look at it, and there's a grow house. Well, if you do CVR, you're going to exacerbate the problem. And so there's different things out there that kind of hinder you from doing it. And you have to go out and fix those problems. If you have a small number of problems, you can fix it. If you have a high number of problems, it becomes too expensive. So for the next few years, we're actually installing a distribution management system, which is a huge effort, tens of millions of dollars. And that will improve our CVR capability, and that we will be able to have the controls. There are products out there right now that optimize CVR for utilities. So this technology is available. And all I would say is that each utility needs to do their own analysis to determine whether CVR will work for them, where it will work, and at what levels. So with that, I will wrap it up and turn it back over to Steve.
Okay, well, thank you, Jim. And we're going to turn pretty quickly here to our last presentation to make sure we have enough time to get through all that. But I did want to just ask you real quick, one of the questions that came in, is there a publicly published study of your of the program that you just described at SMUG?
Yes, there is. I'm trying to remember if we posted it on the smartgrid.gov website. I believe it's posted there. If not, I could either send it to you and you could send it out, or someone could email me. My email address is on this last slide.
Okay. We might, maybe I'll try to get that from you and include that in one of your slides that we post on the website. So thanks, Jim.
All right.
So our next speaker who will conclude in talking about the M&V for CVR and VVO is Josh Rustin. Josh works as a statistician for the Northwest Power and Conservation Council's Regional Technical Forum, and he previously worked for consulting firm Cabinets' Energy Services Division. He specializes in research design, impact evaluation, and energy modeling. And he learned about CVR and VVO when he managed the RTF's process for reviewing stakeholder feedback and updating these protocols that have been developed. And he has his PhD in mathematics from the University of Wisconsin. So Josh, I know we're getting towards the end here, but if you can maybe take the full time we have remaining to go through your presentation, that would be great. Thank you.
Okay, thank you, Steve. Well, it's great to kind of start off with such good context. Okay, sorry, my animations aren't what I thought they were. So just very quickly, what are these measures about? The people have already said this, but I kind of just wanted to put it in my own terms. So some things use less energy at lower voltages, and we've seen a bit about how that's kind of unfathomable to kind of estimate what your net effect is going to be from first principles. But some things use less energy at lower voltages. So I have here this little graphic kind of cartoon of what might be going on at the voltage level along the feeder. And the idea is that the voltage level does drop over the course of the feeder, and that in this example here, some customers are probably a little bit getting a little bit too high voltage in the blue case, and might be going a little bit lower than is allowed in the red case. But there's when you lower the voltage, it lowers voltage along the feeder, not necessarily by the same amount at every point, but it lowers voltage along the feeder, and so there's energy to be saved. The two complications to estimating how much energy is saved are, number one, that average change in voltage can be hard to estimate. Maybe not so much if you have the right kind of smart meters and are able to toggle perform some sort of automated control to your distribution, so you turn the CVR kind of on and off, raise and lower the voltage, similar to the slide study. But in a lot of cases, they don't have that. So this knowing what's going on, what kind of change in voltage your customers are seeing all along the line can be difficult. The second complication is that the saving factors themselves, those depend on the end-use mix that customers have along the line. We've luckily had a lot of conversation about that already. This is another plug for this P&L study. It's just a neat study to look at. It's got, they actually tested a lot of different kinds of equipment in the lab to see what its response was to changes in voltage. And then another study that's been mentioned, the NEA distribution efficiency study, that actually goes out and empirically measures these at a lot of houses. So they're raising and lowering the voltage. They have meters at the houses, and so they're measuring the change in energy consumption associated with those changes in voltages directly. So that kind of is a snapshot of the savings factors, at least around the time the study was conducted. So I'm going to want to talk about two different protocols that the RTF has worked with and developed. The first is one that we call the simplified VO protocol. So the simplification here is that it leans on this kind of canned savings factors, the ones that were derived from that NEA study that I just discussed. These factors, they're in tables in the protocol. They vary by climate, air conditioner saturation, electric resistance heat saturation. And importantly, they are actually based on data that's collected at the residential end users. So it's capturing savings on the customer side of the meter. This is one point from that. So any savings that might occur on the utility side of the meter, those are left to kind of modeling and engineering estimates, at least from the perspective of this protocol. Also, of course, they apply to mostly residential feeders because that's how the study was conducted. You can kind of extend them to ones maybe that have some more, say, light commercial in there, if you have it, depending on what you know about them. This protocol, I should have mentioned this here. It's a kind of what we call proven status and active right now at the RTF, just meaning that the RTF kind of stands behind it right now, considers it reliable. The second protocol is one that we call the automated CVR protocol number 1. So some of these names are a little bit historical, but the automated is important. This protocol estimates the savings by actually having the practitioner alternate CVR on, CVR off, day on, day off, and use the data collected from that to empirically estimate the project-specific savings factors. So the idea here is that this one directly measures the kind of switchable savings. Okay, so that's an important component, important aspect there too of this. I think someone had asked a question earlier, maybe just in the comments, about how the utility gets credit for this when some of this is happening kind of in the distribution planning side of the business, but the benefits are showing up in energy efficiency. And some of the benefits here we're not able to get. You have to model those. The factors in the CBR protocol, those are based on actual feeder level data, so not data collected at the end users. So it does actually capture savings on both sides of the meter. Again, just the part of the savings that's actually switchable on and off. The administrative status at the RTF for this one is deactivated. And I want to be clear that only means that it doesn't really provide any useful simplification for people. That was the RTF's intent in deactivating. We don't want to maintain it. If people are going to do this kind of approach, they should probably do it within a custom evaluation framework. So that's just kind of an administrative thing, and it doesn't mean that we're trying to say the protocol is somehow unreliable or anything like that. One big theme in this work for sure is that it's very difficult in setting up protocols for estimating savings to find the right balance between flexibility, reliability, and ease of use of the protocol. So it's a recurring theme. So a little more details on the simplified VO protocol. And before I go into this, I'll mention there are a couple of places here where I'll be alluding to some additional slides. Those are at the end of my presentation, and when the presentations are posted online, those will be available to look at if you're interested. Okay, so this one, the simplified VO. So just to give a sense of the sorts of projects, sorts of systems where this would be applicable, this is the one that uses the canned VO factors. So those are residential specific, so it's restricted to residential and mostly commercial loads on those systems. You'll need to be able to collect some data on each affected feeder. That's hourly averages for a week pre and a week post, the way we have it written. That data is not that hard to collect, though. You don't have to keep your acquisition hardware in place forever. It's just during the evaluation period and some checkup periods later for persistence. So that's not really a hard restriction. And finally, we have performance thresholds. These have one of the big roles of these is they first help define the baseline, so that the savings is being claimed relative to a system that could have lasted for a while. It can't be a system that needs all kinds of substantial improvements, and it would have probably been, had changes in the near future anyway. We wouldn't want to claim savings relative to that. At least as importantly, though, these performance thresholds are intended to help ensure that the voltage drop over the course of the feeder is linear. So if you have a total voltage drop between source and end of line of, say, 5 volts, then halfway down that, you've got about half that voltage drop. That's important for kind of extrapolating the delta V that's being seen by the customers. And if you have a system that's kind of all over the map, those calculations just don't work. Or at least the simplified versions of them don't, that are baked in the protocol. The performance thresholds also help protect against low voltage issues. Tom mentioned that earlier, that again, you need to know what's going on all along your feeder, and when you lower voltage at the source, somebody close to end of line might be experiencing problems. So your measure wouldn't last very long. Probably then they would complain. Okay, and I kind of touched on this already. These performance thresholds help validate the assumptions that we need to, number one, extrapolate what's from source and end-of-line observations, what's going on throughout the feeder, and number two, when we go to annualized savings from the evaluation period to the full year, we need to take some assumptions there. I won't say much more about these performance thresholds. There are things like power factor, load balancing among 3 phases, voltage drop, and there are details in the additional slides. Okay. I've alluded to this, I guess, already. The basic idea of this protocol, this is the simplified one, uses these canned VO factors from the NIA DEI project, or load research project it's called here. You also see it, it lived under something called the Distribution Efficiency Initiative. I suggest that maybe it's a Google search term if you're trying to find this document. These VO factors, they vary by climate and the saturation of air conditions and electric resistance heat. And as I said before, they reflect the residential end use mix at the time of the study. So the intent here really is simplification. That's the main goal of this protocol. And to I'm getting myself lost here. Yeah, so we know some things that come along with that simplification. One, that these savings are only meant to be right on average. Okay, you can't expect the VO factor from a table, as the SMUD study shows. You can't expect that to necessarily apply to every one of your feeders. So that kind of right on average is something that the RTF finds to be acceptable for savings claims within the regulatory process, and whether or not that's an acceptable standard for, say, capital improvement case on a grid improvement project is, the RTF doesn't have any comment on that. And finally, again, the savings that happen on the distribution on the utility side of the meter, those are calculated separately, and we don't say how to do that. If you're actually engaging in a project, there's all kinds of things that could be going on, and you're probably going to need to get into some non-trivial modeling. So trying to spell that out in the protocol from the RTF is maybe not helpful. So the tricky part here, and I guess one of the things that's making it tricky, well, is the VO factor is only useful if you can estimate the delta V. We've said that a couple times now. Because percent savings is just the VO factor times percent delta V. So what we're trying to get at when we say delta V is the average annual change in voltage being experienced by the end users. Okay. So how can we estimate that with only, say, a week of data or something, a week pre and a week post? and data being collected only at source and end of line. Well, that's the tricky part. So it's easy to estimate for these very linear systems, but of course, as I said, voltage drop along the line isn't necessarily very linear in practice. So we use the system performance thresholds to increase linearity, but they can sometimes they can be very restrictive in terms of eligibility. And some of our stakeholders, that causes problems for us to have a protocol out there that they can't actually apply. And they have to answer a lot of, why aren't you doing the RTF protocol? And we tried to explore the question about whether there's a way to get to relax those and still have reliable delta V estimates. And our answer is probably wound up somewhere around probably sometimes, but nothing we can really make into a protocol. So the RTF's kind of path on this that was to describe kind of a benchmark method and the specific circumstances where the RTF judges savings to be reliable. So the benchmark method is satisfying all the performance thresholds that we just described, so that we're assured of linearity, and they help assure some other areas, help give us assurance on some other topics. And to permit deviations from that, they just point out what validity threats have to be addressed when those benchmark circumstances fail. So when BPA engineer we talked to described this as kind of putting lines on the regulatory playing field. We're not always going to be able to meet all those restrictions, but I need to communicate to the regulator, okay, here's where we stepped out of bounds, and this is the sort of thing that we need to describe why our responses to that are reasonable. So we spelled out kind of 4 areas for potential validity threats. Extrapolation, that's from what's going on at source and end of line to what's going on along the feeder. The baseline is clearly defining the baseline system configuration as being something that actually could have kept operating like that for a while. Annualization, if you do your metering, your data collection in the fall, then how do you annualize to what's going on in the winter, summer? And persistence. Is this something where you're going to be causing low voltage events for some customers and have to walk back your voltage reduction? So that was how we with the RTF kind of navigated the different kind of stakeholder concerns. And I know that's when I was putting this together, I was worried that might not be quite of interest to everybody, but it just became central to us. The technical things to do is one question, but how to make it work for the different stakeholders, especially when you're talking across departments and utilities. It's not just energy efficiency people, it's also distribution engineers. This kind of political aspect of the solution became kind of central. So one thing that was pointed out to me by a BPA engineer recently is if we were doing this all again, we might do some things differently, partially because it's just a lot easier to get the data nowadays. Working with cellular transmission data, but also there are a lot of vendors now starting to occupy this area, and they have some sophisticated models that seem credible to some people at least. Okay, so that's the simplified VO, our kind of simple protocol. I just want to say a few words about the automated CVR. I think this is much more similar from what I think Jim said, much more similar to what SMUD was what they were doing. I can't say that for certain. I'm not familiar with that study, but just based on the slides. So this is our second protocol. It's not the simplified one. It's the one that requires you to be able to switch the grid, your voltage optimization on and off. You raise and lower the voltage daily. The eligibility, that still has some restrictions, at least the way our protocol is written. But again, it's a deactivated protocol, so the ideas are there. But people, we're really asking the RTF doesn't want to try to maintain and stand by behind it. So partially because of the controversy with system performance criteria, trying to spell those out in advance. This one, since you're directly measuring the voltage factors along the feeder, you're no longer restricted to residential only. So any kind of, basically any kind of loads are fine. The big restriction is you actually have to be able to control the voltage levels in an automated way so that you can day on, day off kind of toggle the measure. There are some places where you have to do some kind of load flow simulation modeling for the extrapolation and annualization. The data collection requirements here, so for each affected feeder, hourly values for 90 days, alternating CBR, CBR on, CBR off. Voltage, that's a source and end of line by phase. Power and reactive power, just as source for those two. So performance criteria, again, those are spelled out in the additional slides. The reasons for having them are similar to the simplified case. Okay. For this one, the savings method summary is pretty straightforward, really. So we collect the data, 90 days on and off. And then based on that data, we empirically estimate the savings factor for each feeder. We'll do this separately for every time the protocol is used. And keep in mind, these factors actually do capture savings on both sides of the meter because of just the way the research is constructed. But also importantly, it only can measure this sort of switchable savings. So if you have kind of hardwired system improvements that are part of the project, you have to estimate any savings due to those separately. And finally, of course, the energy savings is estimated as the product of the savings factor, annualized average delta V, and annual baseline kWh. Okay. And I put together some references here that I found useful while I was looking into this. That's the end of my presentation, Steve.
Okay, well, thank you, Josh, for doing that. And as you mentioned, there's a number of additional slides with background on the methodologies and the approach that will be available in the package that we'll put up on the website. We have reached the end of our allotted time for our webinar today, so we really don't have much time at all for questions that came in. I think we got most of them answered throughout the webinar. There were a few questions in terms of the regulatory policies, in terms of providing credit for utilities with respect to the savings that occur. We're not necessarily going to be covering those types of policies and the reimbursement for utilities on this webinar, but if I can find some ready resources, we'll try to post those on the webinar site associated with this one in particular. I do, Tom, if you're still there, I do want to see if you might want to respond to one question that came in, or Jim as well, in terms of how you see the CVR and the VVO interacting with all the grid edge, the distributed generation and other strategies, storage and such on the grid. So I don't know if you have like the 20-second version of comments about how you see that working together. I know, Jim, you touched on that with the DMS.
Yeah, I can see. Oh, you want to take it, Tom?
Oh, I can just say I'm interested in that answer too. I think it'll work with distributed generation. It might just need a better control system because the natural way you would have distributed generation is it wants to raise voltage. So both Jim and Josh showed slides of voltage going down. Well, distributed generation can flip that and push voltage up, or at least moderate the voltage drop. So if you end up with having distributed generation where your voltage is already low, it can help CVR. But if it's somewhere else, it may hurt it. So it's just a matter, I think, of getting more experience with it, but it might need a better control system to make it work.
I agree with that. I think what you're going to see is the development of what we call a DERMS, a Distributed Energy Resource Management System. And there are versions of DERMS out there right now, but I don't think they've hit the real, I don't know if they're fully functional at this point. And I think when you have the ability to control, the thousands of different potentially end-use devices and the photovoltaics, the storage, the electric vehicles, energy efficiency, demand response through a DERMS, I think you'll have the ability to optimize your CVR. So I think you can still do it. It's just a matter of having that control and that visibility.
Well, I think that's an excellent note to end our webinar today on the upswing of the future and all the opportunities be there. I want to thank Tom, Jim, and Josh for your presentations and the Department of Energy for funding this. As you can see up on this last slide, there will be more webinars to come, and the slides and the audio from this webinar will be posted for your future reference well into the future. So again, thank you, and you all have a great rest of your day.